Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're going to tackle a practice problem set that relates to our lecture on separations and purifications. Let's go ahead and get started with problem number 1. Problem number 1 says, fractional distillation under atmospheric pressure would most likely be used to separate which of the following compounds? Before we look at the choices, let's recall what fractional distillation is best used for. It's used when two liquids have boiling points that are close together, specifically less than 25 degrees Celsius apart. The fractionating column provides repeated vaporization, condensation cycles, which helps separate liquids that would otherwise be difficult to isolate with simple distillation. Keeping that in mind, let's go through each option. A says methylene chloride, boiling point of 40 degrees Celsius, and water, boiling point of 100 degrees Celsius. That's a difference of 60 degrees Celsius, which is too far apart for fractional distillation. You just use simple distillation here. Choice B says ethyl acetate, boiling point of 77 degrees Celsius, and ethanol, boiling point of 80 degrees Celsius. That's a difference of only 3 degrees. These boiling points are so close that you must use fractional distillation to separate them effectively. And this is exactly what fractional distillation is designed for. In fact, B is the correct answer. Choice C says aniline, boiling point of 184 degrees, and benzyl alcohol, boiling point of 205 degrees. Now, that's a 21 degree difference, and that's within the right range for fractional distillation. But remember, we're distilling under atmospheric pressure. These boiling points are very high, especially for organic liquids. Whenever the boiling points are over 150 degrees Celsius, we usually consider using vacuum distillation instead to avoid degrading the compounds with excessive heat. So that's why C wouldn't be the correct answer. Choice D says aniline, boiling point of 184 degrees Celsius, and water, boiling point of 100 degrees Celsius. That's an 84 degree difference, too large for fractional distillation. And again, the aniline is too hot for distillation at atmospheric pressure. So this would call for vacuum distillation or maybe even an extraction depending on the mixture. So putting it all together, the best answer is clearly B because the two liquids have boiling points that are close together and they're well suited for fractional distillation under atmospheric pressure. Let's move on to problem 2. Problem 2 says, which of the following compounds would be the most effective in extracting benzoic acid from a diethyl ether solution? To figure this out, we need to remember how extraction works, especially when dealing with acid-base chemistry. Benzoic acid is a weak acid. In organic chemistry extractions, weak acids can be pulled into the aqueous layer if they're deprotonated. That is, if we convert them into their conjugate base form. The conjugate base is ionic, meaning it's water soluble, and that allows us to separate it from the organic solvent, in this case, diethyl ether. So our goal is to add something that will deprotonate benzoic acid, turning it into the benzoate anion, which will then move into the aqueous layer. Let's go through each answer choice. A says tetrahydrofuran, or THF. That's an organic solvent, not an aqueous solution. It's not going to interact meaningfully with benzoic acid in a way that helps extract it. So we can go ahead and eliminate that. Choice B is aqueous hydrochloric acid. Hydrochloric acid is a strong acid, and since benzoic acid is also an acid, adding more acid isn't going to deprotonate it. In fact, this will just keep benzoic acid in its neutral form, which stays in the ether layer. So that's not going to help either. Choice C is aqueous sodium hydroxide. Now this is our winner. Sodium hydroxide is a strong base, and it will react with benzoic acid to deprotonate it. This forms the benzoate anion, which is water soluble. And once that happens, the benzoate will transfer from the organic ether layer into the aqueous layer, allowing us to isolate it. So C is our answer. Let's still work through D. D is plain water. And while water is polar, it's not basic enough to deprotonate benzoic acid. That means most of the benzoic acid would actually remain in the organic layer, so water wouldn't be effective here. Once again, the best answer is C, aqueous sodium hydroxide, because it converts benzoic acid into its water-soluble conjugate base, and it allows for effective extraction into the aqueous layer. Problem 3 says, which of the following would be the best procedure for extracting acetaldehyde from an aqueous solution? When you're doing an extraction, especially from an aqueous solution into an organic solvent, the efficiency of that extraction depends on how many times you extract and how much solvent you use each time. A really common misconception is that doing one big extraction is better than doing several small ones. But that's not true. In fact, it's the opposite. Multiple small extractions are more effective than a single large extraction of the same total volume. Why? Well, because with each extraction, you're removing a portion of the compound. But the more you repeat the process, the more total compound you recover, especially when the partition coefficient isn't in favor of one phase over the other. So let's walk through the options. A says a single extraction with 100 milliliters of ether. B says 2 extractions with 50 milliliter portions of ether. C says 3 successive extractions with 33.3 milliliter portions of ether. And D says 4 successive extractions with 25 milliliter portions of ether. Based off of the logic that we discussed, answer choice D is the correct answer. So we have 4 successive extractions of 25 milliliter portions. That still adds up to 100 milliliters total, but by dividing it into 4 steps, you give the ether 4 chances to pull acetaldehyde out of the aqueous solution. And with each round, you're pulling out a fraction of the remaining amount, not just what was left from the very beginning. So this leads to greater overall recovery of the compound. With that, we're going to move into problems 4 and 5, where we want to refer to the given table. So here we're given 4 compounds and their associated RF values in ether. Problem 4 says, what would be the effect on the RF values if thin layer chromatography were run with hexane rather than ether as the eluent? To answer this, we need to think about how eluent polarity affects RF values. In thin layer chromatography, the stationary phase, usually silica gel, is polar. The mobile phase, or the eluent, can vary in polarity. The more polar the solvent, the better it is at pulling compounds up the plate, especially polar compounds that would otherwise stick to the silica. So if you use a more polar solvent than ether, then the compounds will move farther, giving you a higher RF value. But if you switch to a less polar solvent like hexane, then compounds, especially polar ones, won't be pulled up as well. They'll stick to the stationary phase and they will travel less. So the overall effect is that the RF values will decrease if we switch from ether to hexane. The correct answer for 4 is D. Problem 5 says, if these compounds were separated by column chromatography with ether on silica gel, which would elute first? Column chromatography, like thin layer chromatography, involves a polar stationary phase, again usually silica, and a mobile phase, in this case ether. In this setup, compounds that interact less with the stationary phase, so less polar compounds, will elute first. Compounds that are more polar will stick to the silica beads longer and come out later. Let's look back at the table of RF values. While RF values aren't directly used in column chromatography, they do reflect polarity. Higher RF values mean the compound moved more easily on thin layer chromatography, which typically means it had less interaction with the polar stationary phase and is therefore less polar. The compound with the highest RF value is 1-naphthalene methanol with a value of 0.4. This suggests it's the least polar of the group and it would interact the least with the silica gel. That means it would elute first in column chromatography, so 5 is D. Problem 6 says, 4 compounds, 1, 2, 3, and 4, are separated by chromatography techniques. Compound 3 is the most polar, 2 is the least polar, and 1 and 4 have intermediate polarity. The solvent system is 85 to 15 ethanol to methylene chloride. Which spot on the card below likely belongs to compound 3? Now, this is an example of reverse phase chromatography. The solvent system is polar, which means that the most polar compound will travel the furthest up the card, resulting in the largest RF value. This gives compound 3 the largest RF, which corresponds to spot A. So 6 is A. Problem 7 says, suppose an extraction with methylene chloride is performed with the desired compound initially in brine. In a separatory funnel, which layer will be the organic layer? And in this problem, we're given the density of methylene chloride, 1.33 grams per milliliter, and we're also given the density of brine, 1.04 grams per milliliter. The key thing to remember is that in a separatory funnel, the denser solvent always settles on the bottom, and the less dense solvent floats on top. Methylene chloride is an organic solvent. It's not water-based, and it's immiscible with brine, which is just a saltwater solution. Since its density is higher than brine, which we can tell by comparing the density values we're given in the problem, methylene chloride will be the bottom layer. That means that the organic layer is on the bottom in this extraction. So the correct answer for problem 7 is B. Problem 8 says, silica gel is often used in thin layer chromatography. What property does silica gel probably possess that makes it useful for this purpose? Silica gel is the most common stationary phase in thin layer chromatography and in many other forms of chromatography. And the reason it's so effective comes down to one key characteristic: polarity. Silica gel is a highly polar material. It contains silanol groups, silicon bonded to a hydroxyl group, that can form hydrogen bonds and interact with polar compounds through dipole-dipole interactions and other polar attractions. This polarity is critical in chromatography because it allows silica gel to hold on to polar compounds more tightly, and that slows down their movement. Less polar compounds, they won't stick as well, and they'll travel farther up the TLC plate. And that's how separation is achieved. So looking at the answer choices, A says acidity. While silica does have some mildly acidic properties, that is not its most relevant feature for chromatography. B says polarity, and yes, this is exactly what makes it such a great stationary phase. B is the correct answer. C says specifically sized pores. That matters in size exclusion chromatography, but not in thin layer chromatography. And D says aqueous solubility. Silica gel is not water soluble, and in fact, it's used precisely because it's solid and stable. So once again, problem 8 is B. Problem 9 says a mixture of sand, benzoic acid, and naphthalene in ether is best separated by blank. Let's break this mixture down by the properties of each component. Sand is inorganic, solid, and completely insoluble in ether. Benzoic acid is a weak organic acid, and it's partially soluble in ether, but it can also be ionized and extracted into an aqueous base. Naphthalene is a nonpolar organic compound that's highly soluble in ether, and it stays in the organic layer. Now let's think about how we'd separate them. The first step should be filtration. Why? Well, because sand is a solid, and unlike the other two, it doesn't dissolve in ether. So you can easily remove the sand by simply filtering the solution. Now you're left with benzoic acid and naphthalene, both dissolved in ether. To separate these two, we can take advantage of the acid-base properties of benzoic acid. If we extract the ether solution with aqueous sodium hydroxide, then the benzoic acid will deprotonate, forming benzoate ion, which is water soluble. That pulls it out of the organic layer and into the aqueous phase. Naphthalene, on the other hand, is nonpolar, so it doesn't react with base and it stays behind in the ether. After separating the aqueous and organic layers, we can evaporate the ether to isolate naphthalene. And then we can recover benzoic acid by acidifying the aqueous layer to reprotonate the benzoate ion, causing it to precipitate. Matching this process with the answer choices, we get that problem 9 is B. Problem 10 says, simple distillation could be used to separate which of the following compounds? Simple distillation is best when you're separating two liquids with boiling points that are both under 150 degrees Celsius and differ by at least 25 degrees Celsius. Keeping that in mind, let's go through the answer choices. Choice A says toluene, boiling point of 111 degrees Celsius, and water, boiling point of 100 degrees Celsius. That's only an 11 degrees Celsius difference, not enough for simple distillation. Plus, water and toluene are immiscible, so a better method here would be liquid-liquid extraction rather than distillation. B says naphthalene, boiling point of 218 degrees Celsius, and butyric acid, boiling point at 163 degrees Celsius. That's a 55 degree Celsius difference, which sounds good, but remember, simple distillation should only be used when both boiling points are under 150 degrees Celsius. So this does not meet that criteria. Choice C says propionaldehyde with a boiling point of 50 degrees Celsius and acetic acid with a boiling point of 119 degrees Celsius. This looks perfect. The boiling points are well below 150 degrees Celsius, and the difference here is 69 degrees Celsius, which is more than enough to be easily separated by simple distillation. So this is the correct answer, but we're still going to work through D. D says benzene at 80 degrees Celsius and isopropyl alcohol at 83 degrees Celsius. That's only a 3 degrees Celsius difference between the boiling points. This is way too close for simple distillation. You're going to need fractional distillation here instead. So again, the correct answer for problem 10 is C. Problem 11 says, in order to separate a biological effector from solution, which chromatography technique would be the most effective? When we're dealing with biological effectors, we're typically trying to isolate molecules that interact very specifically with another biomolecule, like a receptor, enzyme, or antibody. That means we need a method that's highly selective based on molecular recognition. Let's consider the answer choices. A says thin layer chromatography. Now, this is a good qualitative method for checking compound purity or even progress of a reaction, but it's not suitable for isolating a specific biological compound from solution. So that's not our answer. B says ion exchange chromatography. This separates molecules based on charge, which is useful for proteins or nucleic acids, but it doesn't provide the specificity we want for isolating something like a specific effector molecule bound to a target. So B is also not correct. C says affinity chromatography. This is exactly what we want. In this method, the column is packed with beads that are coated with a receptor, antibody, or other binding partner that has a high affinity for the molecule we're trying to isolate. So if we're trying to extract a biological effector and we know what it binds to, we can design the column to capture just that effector while everything else washes away. So 11 is C. Now, D says size exclusion chromatography. This separates molecules based on size, not binding specificity. So again, not selective enough for this task. The best and most effective option here is C, affinity chromatography, because it leverages the specific interaction between the effector and its binding target to isolate just what we need from the solution. Problem 12 says, given a solution of insulin and titin, and we're given the molecular weight for both, which chromatography technique would be the most effective for separating out usable molecules of titin? Let's work through our answer choices. A says thin layer chromatography. This is great for separating small organic molecules based on polarity, but it's not practical for large biomolecules like proteins, especially not when we're trying to isolate a massive protein like titin. So we can eliminate this choice. B says ion exchange chromatography. This separates proteins based on charge. And while it's useful in many cases, that's not ideal here because we don't know if the charge difference between insulin and titin is extreme or consistent. And it also doesn't leverage the huge difference in size, which is our biggest advantage in this scenario. C says affinity chromatography. Now, this would work if we had a specific antibody or ligand that binds only titin. But the question doesn't mention anything about a known binding partner. So there's no guarantee that this would give us a clean separation. Finally, choice D says size exclusion chromatography. This is exactly what we want. In this technique, the column is filled with porous beads, and small molecules like insulin are going to get trapped in the pores, so that means they travel more slowly. The large molecules like titin, they can't enter the pores, so they elute first. This makes it the most direct and effective way to separate such a large protein from a much smaller one. So once again, 12 is D. Problem 13 says, the gas eluent in gas chromatography and the liquid eluent in paper chromatography are examples of which component of these systems? The key word here is eluent. An eluent is the substance that flows through the system and carries the sample with it. In chromatography, the eluent is always part of the mobile phase, not the stationary one. Therefore, the correct answer is B. Problem 14 says, during gravity filtration, a student forgets to heat the solution before running it through the filter. After capturing the filtrate, the student analyzes the sample via IR spectroscopy and finds none of the desired product in the filtrate. What likely occurred to the student's product? First, let's recall the purpose of heating a solution during gravity filtration. Heating is often used when you want to keep both the solute and solvent dissolved while filtering, especially if the compound has limited solubility at room temperature. If the solution cools too much during filtration, the product can crystallize out and get trapped on the filter paper as a solid. So it ends up in the residue rather than in the filtrate. That's likely what happened here. By not heating the solution, the product precipitated out before or during filtration, and it stayed on the filter paper. That's why the student didn't detect any product in the filtrate. Now let's review the options. A says the product degraded because of a prolonged filtration time. There's no evidence that the product is unstable or that degradation occurred, so A is not true. B says the product evaporated with collection of the filtrate. That's unlikely. Evaporation would only be a major issue if we were heating a very volatile compound, which we're not told here. So B, incorrect. C says the product precipitated and is present in the residue. That fits perfectly. The lack of heat allowed the product to fall out of solution and get stuck in the solid residue. C is the correct answer, but we'll still work through D. D says the product was dissolved in the solvent. If that were the case, it would have been found in the filtrate, so D is also incorrect. The best explanation is C. With that, we can move into our last and final problem. Problem 15 says, lactoferrin, a milk protein, is a valuable antimicrobial agent that's extracted from pasteurized, defatted milk utilizing a column containing a charged resin. This is an example of which of the following chromatography techniques? The key phrase here is charged resin, because that tells us the separation is based on the interaction between charges on the compound and the stationary phase. And that points us directly to ion exchange chromatography. In ion exchange chromatography, the beads in the column are coated with either positively or negatively charged groups. And these charged groups attract and hold molecules with the opposite charge. So for example, a positively charged protein, like lactoferrin, can bind to a negatively charged resin. Then by changing the salt concentration or pH, the bound protein can be selectively eluted. So the correct answer here is B. And with that, we've completed our practice problem set. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.